Hi people, welcome to the next topic in TOS, and it's the last topic for theory of structures. If you cast your mind back to some weeks ago, where I spoke about a little when I did the introduction, and I spoke a little bit about what we're gonna do in TOS for the coming weeks. And yes, the last topic is at hand. Okay, deflection. Now this note is a PDF. It's on Blackboard under deflection. There's a short note, and it just gives some examples to work through. I'm going to just read through some bits, explain some bits, okay? And I'm going to take one example, number 1, and the note explains the steps to work through to be able to work out the deflection in the beam. We'll explain now what deflection is. But I'll take one and I'll explain and I'll refer to the document as I go along. Right, deflection. As stated previously, lateral loads. Okay, lateral just means like if you have a beam, all the loads acting on the beam. All the loads acting on the beam. If I can maybe just try and draw it if possible. Let me see if I can be smart and do something in PDF. Right, so if we have a beam there like so there, okay, there's the beam over there, and there's the supports there like so, okay, and of course by nature of the member, it's a horizontal member, so loads are acting over there, okay, so of course the beam will want to bend like this, and these loads here, because they act across, if I drew a section of the beam, these loads act across that section there like so. We call that lateral loads. Okay. As stated previously, lateral loads acting on a beam will cause it to deform. Let me just make this a bit smaller. Will cause it to deform in a mode known as bending, which is that over there. It's bending over there. And this vertical displacement of the beam from the straight horizontal line is called deflection. So what the section is going to want to do, we're going to want to be able to work at that distance from there to there. Okay, the distance that this beam drops from there down to there. And that there is called that over there, the deflection. The vertical drop the beam undergoes under load. And of course, I think you know by now that it can't drop meters. Nausea deflection can be anywhere between 0 point something to about 5 or 6 millimeters, depending on the size of the beam, depending on the loads being carried, and depending on the span of the beam from there to there. Okay, but if it's going to be a small number. Okay. Right, as we said before, the stiffer a beam, that is the higher its I value or its second moment of area value, the more it will resist bending and vice versa. We said that in section properties. Okay. There are various methods to calculate this deflection, namely Macaulay's method, which is what we're going to do. Okay. And when you go to S4, when you do indeterminate beams and trusses and frames at S4, you use the moment area method and use strain energy methods. Okay, but for us at S2, we can use Macaulay's method. Okay, right, the relationship between moment, which is capital M, slope, which is theta, and deflection delta. Okay, so that's just the symbols used for moment, for slope, and deflection. Right, bending moment M can be written as that there. Okay, so the moment at X is equal to E times I. Let me make this E times I times d2 dy x squared, where E is Young's modulus of elasticity, which is a known, okay, known factor. I is the second moment of area of that beam, and if you're using steel beams and we go to the steel tables, we'll be able to pick out its Rxx value. Okay, so that's a known value, and this here, it's the second derivative, you know from your maths now, that's d2y by dx squared, where y is the vertical drop or the displacement in the beam, and x is the distance from the end of the beam running along the length of the beam. So y is the vertical drop of the beam in deflection, and x is the distance from A to D in this particular beam, where A is called the origin. Okay, so y is the vertical distance, x is the horizontal distance. Example 1. Calculate the deflection at B and C for the following beam. Okay, also calculate the slope at A. E is given, so that's 200 gigapascals, and I is given as 65.4 times 10 to the power 6 millimeters to the foot. And for a particular beam, we went to the steel tables and we just got that value there from the steel tables. Okay, now people there, I'm going to take this as an example, and I'm going to work to this beam, and following this in the note there is the steps to follow to be able to work out the deflection at B and C and the slope at A. Okay, Macaulay's method. First one there is calculate support reactions. Now if I copy this beam here and I drop it into my board over there, there's it over there. Okay, and I've taken moments about A to find VD, and I've done this already because from here we all know that by now. It's an easy example. So I took moments about A to find VD, and I summed verticals to find VA. So from that there, I did it already because you know how to do it. So VA is 9.25 kilonewtons and VD is 12.75 kilonewtons, given those two loads over there. Right, the next point in the process, next bullet point here, use one end of the beam as the origin. We will use the left-hand end A. Okay, all distances are measured from the origin in terms of x. Okay, what it means? It means that, it means this here. It means, so x is starting over there and is going all the way to that distance over there. It's starting at origin there, and that's x over there. Okay, color there. So x starts there, x gets bigger, 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 and of course x goes from A all the way to D. Okay, and all distances are measured in terms of x. Let me take a moment. So the distance, this force is from D is, we know it's 5 meters, but in terms of x, it will be x minus 3. Did you get that? And the distance, this force is from D is equal to x minus 6. Okay, but we get into that now. Let me go back to the document. Use one end of the beam as the origin. We will take the left-hand end, and all distances are measured from the origin in terms of x. X starting at A and going all the way to the other end over there. Next point there. Take moments about the right-hand end of the beam and formulate an equation in terms of x. This will be known as the bending moment equation, and is written as above stated over there. Okay, right. Let's do that. Okay, we'll come back to that now. So what I'm going to do, I'm going to say we're going to take x is starting here, and we're taking moments about d. So formulating my equation as that over there, okay, with the moment that x is equal to ei d2 dy x squared. So I'm going to say the moment at x, I didn't want that. Moment at x is equal to e I d2y dx squared. Alright, so what I'm going to do, I'm going to take moments about d. Okay, so about d, that's going to be a positive moment, a negative moment, and of course, because v dx through d, it will have no moment effect about d. Okay, I'm going to start from left going to right. So about d, va, okay, so that will be va times, right, so how far is va from there? It is x. Remember, x is starting at A and going to D. X is always the full length of the beam, okay? Minus 10 times, okay? And how far is 10 from D in terms of x? It is x minus 3. X minus 3. You need to think about that. You need to get that right. Minus. Why are these minus? Because they are anti-clockwise with respect to the Oh, sorry, I don't want that there. Minus 12 times. How far is 12 times d in terms of x? It is x minus 6. There we go. Okay, x minus 6. Right, people? So we took moments about d, okay, and we wrote all distances about d in terms of x. So that's v8 times x minus 10 times x minus 3 minus 12 times x minus 6. Right. So that's the first step in the process. Right. Next step, then it says there, integrate the bending moment equation to give the slope equation. So what we're going to do, we're going to take this equation and we're going to integrate it twice. The first integration will give us the slope equation, and the second integration will give us the distance equation or the deflection equation. Right, I'm going to deflect this equation, and it's going to be that, and of course E and I are constants, they don't change. Okay, so if I integrate d2y by dx squared, I'm simply going to get dy dx. There we go. Okay, right, now we need to be mathematics geniuses. We need to integrate. Right, so that's going to be va times x squared over 2 minus d. Right, Macaulay's method rules. Okay, there we go. Macaulay's method uses special brackets. We will be using square brackets. Okay, we'll be using square brackets. So, and when we integrate this, we keep this here. We don't separate it. We don't multiply that. We keep this as if it was a single variable. Okay, so it's x minus 3. Okay, and if I integrate that as a variable on its own, it's going to be squared over 2 minus 12. Notice I'm square bracket, and x minus 6, I'm keeping that as a single variable. So of course that's going to be squared over 2. And of course, out of that first integration there will be a constant of integration, and we're going to call it C1. Okay, let's just see what that's about. Okay, go here. Integrate the Macaulay's bracket as follows. Okay, so keep that as a variable. So if I integrate that, it becomes the bracket squared over 2 plus c. Okay, keep the bracket in this form as if you're integrating a single variable like x or k, etc. Then integrate the slope equation, which we're going to do now. Okay, so that's where we are now in the process. And we need to, I didn't mean that. And now we integrate this another time. Okay, so we need to integrate the slope equation, and that's going to give us the deflection equation, and it looks like so. So the deflection at x is equal to ei remains the same y because they are constants, and of course if we integrate the y dx, we simply get the variable y. Okay, so we need to integrate all of those, so it becomes va times x cubed over 6, yes, minus 10 times, remember the square bracket, we don't separate. Okay, we keep that as a single variable, so that now becomes 3, and it will become over 6 minus 12 times square bracket, we keep it as it is, we don't separate it. That becomes 3, and that becomes 6, and of course that's a constant, so it becomes c1 times x, and of course out of that we get a second constant of integration. Okay, now people notice there we got y as the distance, so we have x as the distance along the beam, we got y as a deflection. Now if we knew x, we could determine y, because we know e and we know I, it's given. But before we can do all of that, we need to determine the constants of integration c1 and c2. I'm going back to my document over there. It says there, then determine the constants of integration. We can call them c1 and c2, which we just did by using the boundary conditions. And what are these boundary conditions? Boundary conditions are points along the beam where we know the values of. Okay, you can read that on your own. And we know that at A, now remember people, the beam will do this under load. It will deflect like that over there. Okay, so we want to work at that distance over there, and we want to work at that distance over there. Okay, so that means at the supports there, the deflection at A and D will be equal to 0. Okay, that means at x equal to 0, y is equal to 0, and at x equal to 8 meters, y is equal to 0. And knowing those two facts, I'm now going to be able to determine C1 and C2. So once we know C1, once we know C2, put in a value of x, which is a distance along the beam. We can determine the deflection at B and C, and it's job done. Okay, right. So let's use those boundary conditions at x equal, where at x at A and x at D to determine that there. Right, so what I'm going to do, I'm going to just clean the board quickly and proceed to find C1 and C2. Right, people, we know that I just rewrote the slope equation. I rewrote it again. Okay, so we know that at A, that means where at the supporter at A, that is where at A x is equal to 0. Okay, and at A x is equal to 0 and y is also equal to 0. Okay, let's go back to that. At A there, x is equal to 0, the deflection is 0. Okay, so what we're going to do, we're going to use that fact to help us to determine C1 and C2. Okay, so if x is 0, I'm going to put this into there, okay, and determine y. So therefore, E I times y is equal to, if that's 0, that's going to be 0. I'll write it for 0 for now. Right, rules of Macaulay. Are you tuning in? You're tuning in. When operating and simplifying the equations where we are now, do not multiply out the Macaulay square brackets. Okay? Next important point. The value inside the square brackets cannot be negative. Okay? If x minus a particular value is negative, okay, then x minus a is set to 0. That's what we're going to do now. Okay? So I'm putting x equal to 0 into every term here. Okay, so that's going to be 0. So x, and so 0 minus 3 is minus 3. So it's 0. So that's going to be 0. Maybe I should just do this. Okay, that's going to be 0. And what's 0 minus 6? That's going to be 0. And what's C1 times 0 will be 0. So all we're left with is plus C2. Okay, so, but we said there that at x equal to 0, y is also equal to 0. Okay, so therefore, that is also equal to 0. So, therefore, C2 is equal to 0. Okay, now that's a bit of a mouthful. But what I've done here, we know at A, x is equal to 0, the deflection is 0. Wherever there's a support, the deflection is 0. We're using that fact, okay? So I'm putting x equal to 0 into here. That's 0. If the bracket's negative, it's set to 0. So that's 0. That's 0. C1 times x, or C1 times 0 is 0. So therefore, and of course, if y is 0, it makes all of that 0. So therefore, from that equation here, C2 is equal to 0. Also, at x equal to d, okay, sorry, my apologies. At d here, x is equal to 8. Okay, so at d x is equal to 8. Okay, and y is equal to 0 because there's no deflection over support there. So what we're going to do, we're going to put x equal to 8 into there, and of course that's going to be 0. So naught is equal to VA, right? VA, but don't we know what? I'll leave it for VA for now. So that is VA times 8 cubed of 6 minus 10 times 8 minus 3, it's 5 cubed of 6 minus 12 times 8 minus 6 is 2 cubed over 6, okay, plus C1 times 8, and of course C2 is 0, but I'm going to write it in for this time. Okay, right, so from here we can work out what C1 is equal to. Okay, do the calculation and check mine before you continue. Alright people, I'm going to write these values out, I think, for the first time. Let me just change the color here. Right, what's VA equal to? VA is equal to 9.25. Okay, so that will be 9.25 times 8 cubed over 6. If we work it out, it will be equal to 789.33. 789.33 minus, if we work that all out there, I get 208.33. Just don't believe me, work it out for yourself. And minus 12 times 2 cubed over 6, I get minus 16, and that will be plus 8 times C1 plus 0. Okay, and of course that's all equal to 0. Okay, and from there I'll be able to work out that C1 is equal to minus 70.625. Okay, so people, now if I look at my equation at the top there, I now know what C1 is equal to, 70 minus 70.624. C2 I know is equal to 0. So now if I know that, which I do, okay, and I know the distance along the beam there, and I know E because it's been given, I know I has been given, I'm now in a position to be able to answer the question. Let me go back to the question quickly. The question there says there, calculate the deflection at B and C for the following beam. Also do the slope. We get into that now. We now know everything. We're now in a position to calculate B and C. Okay. So what I'm going to do, so at B, x is equal to 3. That's it. So at x equal to 3, I'm going to put x equal to 3 into the deflection equation there and determine that over there. Okay, and let me just make some space here quickly. So therefore, at x equal to 3, okay, the deflection at B is equal to E I y, and I'm going to say at B is equal to, right, so that's VA, so that's 9.25 times x is equal to 3. There we go. So it's 3 cubed over 6. Okay, 3 minus 0, so that's going to be 0, so that's out. Okay, 3 minus 6 is minus 3, so that's going to be out. Rules of Macaulay, plus C1, and what's C1 equal to? C1 is equal to minus 17.624 times x, which is 3, and plus C2 is equal to 0. Right. So therefore, okay, now notice from that, I know what E is, I know what Y is, so therefore I can now make Y the subject of this formula. So therefore, okay, we're almost there. Therefore, Y, the deflection at B, is equal to all of that. Okay, work all of that out there, and from all of that there, I get, I'm gonna just write mine down because I worked out earlier, but you need to check it before you continue. I'm gonna get minus 170.250 over, so all of that there is minus 170.25 divided by EI. What's EI equal to? E is 200 gigapascals. Okay. Now remember we did conversions. Yes, you remember it's equal to 200,000 newtons per millimeter squared over I, and what's I equal to? I is 65.4 times 10 to the power 6. 65.4 times 10 to the power 6 millimeters. Okay. Now, are you tuning in? Remember when we started all of this? Okay. We took moments. So that was a force, distance, force, distance, force, distance. Definition of a moment. Then we integrated once and we integrated twice. And of course the units went nuts. Okay. So we need to smooth it all out. We need to convert it all to newtons and millimeters. And at this point here, we multiply all of this by 10 to the power 12. Very, very important. Okay. And that's a conversion factor which converts all of this so that the answer we're going to get there will be in millimeters. There we go. Okay. So work this all out. And from there, we're going to get a minus answer. I get minus 13.02. Okay. So what is that? That's the deflection at B. Okay. So we've answered the first question. The next one that says calculate the deflection at C. What do? We go back to our deflection equation and we take the same equation and we make x equal to 6 meters. We put x equal to 6 into deflection equation, make y the subject of that formula because we know E, we know Y, and we find the value there. Okay, alright, and I'm going to do that. I'm going to clean our board up and do it over here again. Right, there we go. So at C, x is equal to 6. So I'm going to say at C, x is equal to 6. Okay, so I'm going to put x equal to 6 into my deflection equation because we want to work at the deflection. So therefore, E, I, Y at C, what's V? V is 9.25. X is equal to 6, so 6 cubed over 6 minus 10 times 6 minus 3 is 10 times 3 to the power 3 over 6. That will be 0 plus C1. What's C1? C1 is minus 70.625. So it's minus 70.625 times x, which is 6. And of course, plus 0 because C2 is equal to 0. Okay. Right. So from there, I work it all out and I get an answer of minus 135.70. Minus 135.750. You need to work it out and check me, okay? But EIY is equal to that. So Y is equal to, so therefore the deflection at C is equal to minus 135.750 multiplied by my conversion factor, okay, over EI. What's E? E is 200 gigapascal, which is 200 newtons, which is 200,000 newtons per millimeter squared. What's I? I is given as 65.4 times 10 to the power 6. And I work it all out. And I'm going to get a minus answer. And the answer I get there, you need to check me, is minus 10.38 millimeters. Okay, minus 10.38 millimeters. Right. I'm going to flick back to my document there. Let's see. It says here, when operating the last bullet point there, right, you are now in a position to be able to calculate the deflection and or the slope and or the bending moment at various points along the beam for values of x. We just done that. Okay, we calculated the deflection at B at C, and at B x is equal to 3, and at C x is equal to 6. So we answer that part of the question there. Okay, it also says there, also calculate the slope at A. So what does it mean? It means we need to go to our slope equation there and put x equal to, what's the question? It says find the slope at A. What's the value of x at A? X is equal to 0. That means we go to our slope equation there, we put x equal to 0 in the equation there, and make dy dx the subject of the formula, and then we'll be able to determine the slope at A, and that question will be done completely. Okay, so let's do that quickly. And people, before I forget, the question wanted us to work out the deflection at B and the deflection at C. Notice, we got negative answers. Why do you think we got negative answers? Okay, we got negative answers because the beam is sitting horizontally there. Okay, as the beam is loaded, it bends downwards. So that value there was minus 13.02 millimeters. And that value there was minus 10.38 millimeters. Minus 10.38 millimeters. Why is it negative? Because it dropped that amount below the 0 line. Okay, so that's actually before the forms are removed, when the beam, remember in theory of elastic bending, where the beam is truly horizontal, as the form is taken away, as the beam is loaded up, it drops below the 0 line. The minus sign just means it drops below the 0 line. So from there to there is about 13 millimeters, and from there to there is about 10.4 millimeters. Okay, that's why it's minus. Now sometimes we get cantilevers. If I can draw it here quickly over here, if I can just sketch it here. If you got the cantilever, there's a cantilever over there. That beam will bend something like so. The beam will bend something like so, and it'll do that. So even though it's bending down there, okay, that there will be a negative deflection, small little d. And even though the beam is bending downwards over there due to the span and the loads here, the free end of the beam will actually lift off that point there, and that distance there will actually be a positive deflection. Okay, so between the span, almost every time the deflection will be negative, and for the cantilever at the end there, depending on the loads and the length of the cantilever there, the deflection for the cantilever is almost always positive. Even though it's bending downwards, it ultimately rises there because of the beam bending in that fashion over there. Okay, so that's bending below the 0 line, that's bending downwards, but ultimately it's deflecting above the 0 line. Negative deflection, positive deflection. Okay. Right, people, the question there says, we're almost done. Also calculate the slope at A. Okay, so we've done the deflection at B, deflection at D. Using the deflection equation, we now need to find the slope at A using the deflection equation, which is over there. I'm just taking that equation and I've already written it over there. Okay, and what's the value of x at A? X is equal to 0. So at A, x is equal to 0. Okay, so we're going to put this into that over there. Okay, so EI times y times dy dx, that's going to be 0. Naught minus 3, so that's just when it's naught, when it's 0, it's naught. Okay, we set it to 0. Naught minus 6 is minus 6. That's negative, so 0. And what's C1 equal to? Oh yes, C1 is equal to minus 70.625. Minus 70.625. Okay. Alright, we know what E is. 200,000 newtons per millimeter squared. What's I? I is 65.4 times 10 to the power 6 millimeter to the fourth. So therefore, if we make dy dx the subject of the formula and put all the values in, we can determine the slope at x, and that will be job done for that beam. So therefore, dy dx is equal to minus 70.625 over EI. What's E? E is 200,000 newtons per millimeter square. What's I? I is still 65.4 times 10 to the power 6 millimeters to the fourth. Right, people? Conversion factor. Remember, when we took moments here, that was the force times the distance, force times the distance, force times the distance, and so on there. And then we integrated twice. Okay? And we went nuts there to sort all of that out. At this point here, are you tuning in? To smooth that all out, we multiply by 10 to the power 9. Okay? And the answer we're going to get there will not be in millimeters, it's an angle, will be in radians. An engineering angle, we almost always measured in radians. Okay? So if you work all of that out, work it out there, check my answer before you continue. Alright, people, the answer I get there is minus. Why is it minus? Because it's minus. Okay, answer is going to be minus. And it's going to be a small number. It's going to be a small number. 0.005. You can either work to 4 or 5 decimal because it's very tiny, or you can write it in scientific notation as 5.4 times 10 to the power minus or whatever. Okay, so it's a small answer and it's in radians. Okay, so and the reason why it's minus also is because if we go back to there, okay, now remember the slope there, if I take that point there and I draw a tangent at that point there like so, okay, so that angle there is considered to be a negative angle. Okay, so if I measure the angle in radians of the slope of the tangent at that point there, because it's measured that way, is termed a negative angle. So the answer there is minus 0.00540 radians. It's an angle, it's not degrees, it's not in millimeters, it's in radians. Okay, so people, if I go back to my problem there, there's the question again there. So what did I do? I use x as my origin, going from left to right. I took moments over d. I set up my bending moment equation where the moment in x can be written as e times I times the second derivative of y with respect to x. Then I integrated twice, and then I use my boundary conditions. That means at the supports there where I know the deflection at a and d is equal to 0, and I use that fact to be able to determine the constant of integration c1 and c2. And once I did that, I could now go ahead and find the slope at b and the slope at c using the deflection equations. And then I could use the let me go back there. Then I could determine the deflection at B and C using the deflection equations, and then I could determine the slope at A by using the slope equation. Okay, people, that's a lot. That's going to be a big question in the final exam. I'm now going to do 1 or 2 more beams where the beams might have a cantilever, where it can have a UDL, and I'm going to set up the bending moment equation and work to the, I'm going to integrate twice and follow the same procedure for another beam or another 2 beams. Okay, and I shall see you in the next video.